everyone. I am here with Allyson Ettinger. Allyson is an assistant professor at the University of Chicago. Allyson, welcome to the TWiML AI podcast.
Thank you so much. Hi.
Hey, I'm looking forward to digging into our conversation. We'll be talking a little bit about your research and computational linguistics and NLP and a bunch of cool things. But before we dig into those topics, I'd love to have you share a little bit about your background and how you came to work in the field.
Great. Yeah. So I originally came from a background in linguistics and psychology, interested in language in humans and how language works in the brain. So I worked in a lab, a cognitive neuroscience lab, looking at processing of language in the brain for a while. I began my PhD in linguistics with a bit of a focus on psycholinguistics. But fairly early on, I took a strong interest in the promise of computational linguistics as a way both to use methods to continue exploring questions about the brain, but also to ask interesting questions about how to apply puzzles in language to engineering applications and to design of artificial intelligence. And so this was what sent me in this direction of being what I am today, which is simultaneously someone who works on natural language processing and artificial intelligence, and also someone who continues to work on modeling of cognitive processes pertaining to language.
Oh, that's awesome. I think folks who have been listening to the show for a while will recognize that as a recurring theme in our conversations. It comes up from time to time, and I always enjoy it. This kind of two-way street between machine learning and neuroscience. Tell us,
Absolutely.
tell us a little bit about your research and how you kind of explore those relationships.
Yeah, absolutely. So for me, I think it's important to be careful. It's something that I say often. I don't want to be interdisciplinary just for the sake of being interdisciplinary. We want to make sure that this is making a clear contribution to one or the other of these fields, and without diluting those contributions. And so, what I have found to be one of the, in terms of contributing to the to artificial intelligence, something that I have found to be really a genuinely critical and very valuable source of insight from the neuroscience side has been. Methods that are already being applied to study the black box that is the brain, right? So we have a lot of questions about how the brain operates, what types of competencies, what types of processes and mechanisms underlie the outputs that we're seeing. And so folks working in cognitive neuroscience and psycholinguistics have been designing methods that are controlled in various ways for a long time now to try to address these questions. And we're finding now that we have very similar questions about these black box systems that are emerging in artificial intelligence. And so while we do have slightly different questions often in terms of the way that we ask questions about the brain versus about AI, I think there are a lot of really useful things that we can draw, methods and insights that we can draw from the work that we do studying humans to improve our ability to assess the competencies of AI.
Mm. Can you give us some examples of the way we approach this from a study of the brain perspective?
Yeah, absolutely. So, I have two main examples. Back in 2016, I proposed that we take a method that had been used to study encoding of certain types of meaning information, in particular semantic role information, who did what to whom in the brain. And this was a method that made use of simple classifiers to test whether simple classifiers and classification tasks that are designed in a particular way with controls of the syntactic structure of the sentences to abstract away from syntax and target the meaning. This was used to study how and where semantic role information was encoded in the brain. And I suggested that we take this same type of controlled classification-based probing approach and use this on sentence embeddings, sentence vector representations produced by
Mm.
encoders in NLP. And this ended up being very similar to what now is quite a popular approach referred to as probing, classification-based probing. There are a variety of ways that we talk about this. But a key difference in what I proposed there, and a key difference in terms of what comes from the brain side, is rather than just throwing a bunch of sentences and classification training items at the classifiers, one of the key components of the way that this works in the cognitive side is that we control variables to make sure that we aren't testing for something other than what we're trying to target. And so, for instance, we have a controlled variety of syntactic structures to make sure that there isn't some confounding variable in terms of the syntax that the classifier might be picking up on instead. So, for instance, if the classifier if it learns to do the task, and we conclude from this that the relevant information was encoded in the representations, but actually the classifier was just picking up on the fact that in the positive labeled items, the first word is always the, and in the negative labeled items,
Mhm.
the second word is always cat. Then this is a huge confounding variable, and it doesn't tell us anything. And this is a challenge that we see over and over again with our evaluations. There tend to be additional variables that we didn't intend that the models pick up on that obscure our ability to evaluate what's going on. So this idea of control of confounding variables is something that is very well established within the fields of cognitive neuroscience and psycholinguistics, maybe a bit less so on the AI side, but I think it's something that will be of significant value, and it's something that I apply consistently in my own research.
That's a really interesting notion. So, on the machine learning and deep learning side, we tend to think of a lot of the challenges we encounter in understanding these models coming from the idea that these models are so great at pattern matching, and they can match these patterns that are correlated to inputs as opposed to expressing the outputs that we're looking for. And it kind of sounds like you're saying that, well, the brain has aspects of that too, and as brain researchers we have to do a lot of similar types of controls. It's not unique to deep learning.
Absolutely. Yeah, that's a really nice connection there. It's absolutely the case that the brain also may respond to variables that we didn't intend. So often with experiments in the brain, we're giving some type of stimulus, we're measuring brain activity in response to the stimulus, and then we're trying to draw conclusions about how our particular manipulation affected the brain. However, if there are other variables that were influencing the way that the brain responded that we weren't taking into account, then absolutely, just in the same way that we can with machine learning and with NLP, we can draw conclusions that are mistaken because we didn't realize that these other variables were having an effect.
Mm-hmm. And so, in the example that you gave and that problem setup, you were applying a machine learning classifier to brain. Was is this signals or human questions, responses to questions? Take us a little bit deeper into the setup there.
Great. Yeah. So I should clarify that the inspiration was a type of study that was being done. It was taking brain recordings from humans who were reading sentences, and then it was using the classifier to classify on the basis of those recordings what type of sentence the people were viewing,
Okay.
specifically what was the identity of the agent who was doing the action versus sometimes what was the identity of the patient. So this was a study that uh, made quite a splash. It yielded some really interesting results in terms of identifying sort of how and where the brain may be encoding information about who did what to whom, critical meaning information in any linguistic input. For me, what I was doing was taking sentence encodings from NLP models and treating those much like the brain recordings. So you could think, if we think of the NLP model as a brain, it's producing a representation of its input. This is a sentence embedding, and this was being used as input to the classifier instead. And so then the key question is, can we successfully train a classifier to do the task? If so, then we're going to conclude that the critical information for doing the task was extractable from the sentence representation. And so this is how we try to draw conclusions about whether this information was encoded, at least in an extractable way for our classifier.
So the idea is that the your sensor recordings, like a EKG or maybe
It
a
was fMRI in the case of the study I
fMRI.
was mentioning.
Okay.
Yeah.
Um, you've got these sensor recordings. Ultimately, they're turned into a vector that has an abstract relationship with what's happening in the brain. The embeddings have an abstract relationship with the sentences that you're looking at, and you're trying to apply the same technique and see what happens.
Yes, exactly. In both cases, you have a vector which represents an encoding of some kind, a representation that is evoked in response to the input. and we're trying to probe to see what types of information we can extract from that, what seems to be encoded there.
And what'd you learn with that?
So, in the case of the study that grew out of that particular inspiration, and this was a couple of years ago now, my focus was on trying to establish the extent to which these sentence encoders were able to systematically capture compositional information about what's going on in the sentence. And I focused on two main questions, really fundamental types of information in sentence meaning. The first was semantic role, directly inspired by the brain study. This was who did what to whom, and then the second one involved negation and seeing to what extent can the model, to what extent do the representations encode systematic information about what happened and what did not happen. If you have a Bobby went to the store, Bobby did not go to the store, right? Negation tells you things about what happened and what did not happen. So the biggest challenge was to control for, just as I've been discussing, control for variables that may allow the classifier to do well without it having picked up on the actual meaning information, right? We don't
Right.
want to have certain things that are giving clues that the classifier can pick up on. As you said, these classifiers are great at pattern matching. If there's some other pattern in there that's going to help it do the task, then it will, and then we'll learn nothing about what we wanted to ask about. And so basically the way that we did this was to generate synthetic data for which we could control the distributions of all of these different types of variables. The key question here is, can the classifier label whether word X was the agent of word Y? So in a sentence like, Billy went to the store, did Billy do the going to the store? Or Billy hit Bobby, which one did the hitting, Billy or
Mhm.
Bobby? This is the key question. And you would think that this is a very simple type of information, probably one of the most obvious types of information to be encoded in a sentence representation if it's capturing meaning. But what we don't want is for the model to be able to seem like it's capturing that information when in fact it's only capturing what's likely to happen and not what happened in this current sentence. So to give an example, we can have a sentence, the waitress served the customer, or we could reverse those and have it be the customer served the waitress. The second sentence is very strange. Statistically, it's very unlikely. But it's still a sentence that I can say to you and you can understand, and an English speaker can understand, even if it's an odd sentence. And this is the sort of the critical way that compositionality works in language. Humans can understand sentences even if they are unlikely. And this is the place where we may see some really fundamental divergences between models that are trained based on distributions of ideas in text versus models that systematically extract the meaning from any sentence, no matter how strange or unlikely it is. So for this reason, we controlled these types of variables such that models, for instance, that are only based on averaging of word representations and don't have any access to word order are only going to be at chance level performance. So this allowed us to give sort of a reality check to make sure that we're controlling for word level variables that may give clues
Mm.
that don't indicate that because again, the waitress served the customer served the waitress have identical word content, but they mean
Right.
very different things.
Right.
So these are the types of controls I'm talking about. Once we exerted these types of controls, basically what we found was the models classifiers trained on the representations produced by the models performed only marginally above chance level performance, suggesting that really this was not being captured to the extent that it looks like semantic role is being captured in these representations. It's probably more an artifact of the fact that the models pick up on sort of what is statistically likely, and those are types of sentences that they're likely to encounter when being tested.
Hmm. Yeah, we've talked about on the podcast. I think what is a very closely related, and I'm not sure if it's more specific or if it's a subset or superset, but the idea that um, in question answering data sets, you have models that will pick up on kind of spurious correlations that aren't really inherent to answering the question. And here, what you're doing in some ways is a subset in that the questions you're answering is about one specific type of semantic relationship. But it's also, as you pointed out, kind of abstracted in a way in that the models don't get as much information, and the information that they get masks a specific type of I don't know if you would call it noise or relationship, but the word order in particular. And so um, you are kind of taking that out of the equation for the model, and you found that the models probably are picking up on spurious correlations.
Yeah, absolutely. I can imagine a version of our test. We didn't try this in particular, but you can imagine a version of our test that's less carefully controlled that may show very high accuracies, which would, you know, lead us to believe that the models are great at semantic role. And I think this often happens with sort of standard semantic role labeling data sets. This is an existing task. But if we don't control for these types of confounds, then we will end up concluding that semantic role, for instance, is solved or some version of this conclusion, when in fact, the systematicity, this sort of critical building block of being able to understand language, no matter how odd the sentence is, that may well be missing if we don't try to disentangle sort of the model's statistical competency from their ability to systematically extract the representations.
Awesome, awesome. And so that general line of research is looking at, taking things we've learned and studying the brain and applying them to machine learning, and that's a topic or related to a topic of ICLR panel or debate that you're participating in that's focused on this question of how can findings about the brain improve AI systems. Tell us a little bit about the idea with that session.
Great. Yeah, I think this is sort of for a long time, folks have been intrigued by the possibility that we can use inspiration from the brain to improve artificial intelligence. And this is a very reasonable uh, way to think about things because, of course, the human brain is the only existing system that actually has intelligence. It's certainly the only existing system that does language. There are certain types of tasks where artificial intelligence uh, or other types of models can outperform humans, certainly. But in terms of sort of the fundamental aspects of human intelligence, in particular language, that I'll focus on language since this is the one that I spend the most time thinking about. There's just no question the human brain is the only one that can do this at the moment. This is not to say, I typically don't go so far as to say that the human brain's solution to language understanding is the only mechanistic solution that could achieve this. But given that we haven't yet found an alternative that is able to, match the human brain, it seems quite reasonable that we should go ahead and certainly consider taking inspiration from the brain in terms of our actual design decisions and the way that we choose our mechanisms for trying to master natural language processing and natural language understanding. Having said that, in practice, what we tend to find, in my experience, is that it is certainly easier said than done to try to take insights from the brain and apply these to artificial intelligence in a way that will outperform sort of the most successful, more general learning mechanisms that typically occupy the state of the art in the field. So it's something that people are very interested in, I think, and I also think that as we continue to understand more about the brain, we may find more opportunities to continue to try to apply mechanisms in that way. But at the moment, it is challenging, and we do find that um, at best, maybe we have sort of pretty high level analogies to types of things that the brain does that aren't very directly modeled after the actual mechanisms that implement those types of things. So the way that I have tended to find is sort of a more concrete and immediately applicable way that brain science can contribute to improving AI is sort of more along the lines of what I've been discussing here, which is using the competencies that the brain has as a standard by which we assess AI. So the human ability to understand language, I don't think there's any question that that defines the standard for what it means to understand language, for what it should mean to achieve successful NLU. And so, in terms of designing our evaluations, I think it's absolutely critical that we look to look to our understanding of human capacity for language when deciding how to assess the quality of our artificial intelligence models. So this is how I usually tend to pitch the immediate and essential value of brain science for AI, in light of the fact that taking brain mechanisms and directly implementing them to improve AI tends to be a little bit uh, maybe further down the road in terms of showing the type of success that we'd like to see.
So your money's on evaluation and assessment and not drawing architectural conclusions from the brain.
My money is on that as something that's already happening and important, and in my opinion critical for having effective evaluations of AI. It's happening now and I think it needs to happen. I am absolutely not discounting the possibility that we can draw really very valuable mechanistic inspiration from the brain in terms of designing our models, but it's not clear that we're quite there yet in terms of outperforming the other approaches that we have by taking that type of approach.
Some folks seem to have um, stronger opinions than others that neural networks and deep learning are brain inspired. Others think that that's very loose. What maybe it's correlated with how intimately you know the brain, but what's your
Probably. um, yeah, loosely brain inspired, right? I mean, like very loosely inspired by basic functioning of neurons and whatnot, but there are major, major differences between the way that a given neural network operates and the way that an actual full brain operates. So, yeah, loosely inspired, I think, is a reasonable characterization. Very loosely inspired is a reasonable characterization.
and ideas like spiking neural nets and things like that, you don't necessarily see it as getting us closer anytime soon.
I mean, there are absolutely ways that we can try to more closely simulate the functioning of a brain. It's not clear to me that, I mean, certainly if we ended up recreating an actual brain, right? There's an endpoint of this process. If we recreated a brain, then presumably, and we did it down to the smallest uh, unit, right? We've just completely replicated all of the machinery of the brain, then and functioning and all that. Then presumably now we would be able to do everything. But there's a giant space in terms of our capability and what's realistic and feasible at the moment, between current neural nets and baby steps trying to slightly more resemble the brain versus fully replicating a brain. And so,
Mhm.
sure, at the end point of that process, certainly we would successfully manage to improve AI because we would have replicated the human brain and the human brain outperforms AI. But at the moment, again, I think when we take those steps, we may, in certain ways, in sort of focused areas, better resemble the brain. But in terms of the way that we have set up tasks on the engineering side at this time, I suspect that making those changes would end up, for practical purposes, reducing performance rather than improving performance. Now, of course, we need to consider whether these improvements and reductions in performance are really uh, being assessed in terms of measuring the right thing. And in many cases, probably not. We already know there are many flaws with our evaluations, and this is, why I think this is an interesting and critical problem at the moment in the field. But these are, there's no getting around the fact that these are the benchmarks that we use at the moment, and there are many other, in many ways, those performance metrics are at least informative if imperfect. So yes, based on the benchmarks that we have currently, I suspect that those, for now, taking these types of baby steps to make the networks more brain like, maybe way down the line could be useful, but in terms of the intermediate steps, I suspect it would be a step backward in terms of the practical uh, performance metrics that we use to measure how what we're doing.
Got it. Got it. Um, Returning to the assessment and evaluation work, um, it is in some ways related to the our desire to have greater explainability, interpretability, understanding of what's happening inside these deep neural networks, or quote unquote black box models. Is that a field that you think the brain study offers some insights into?
Yeah, I consider this work to be squarely within the analysis and interpretability area of NLP. Absolutely. So, I think that analysis and evaluation go hand in hand, because with our evaluations, we're trying to get a clear sense of how good the models are. And I think that how good the models are it connects quite importantly to the model's competence with specific types of phenomena, which often is what the analysis side is doing, is trying to understand what the models have managed to do. Of course, that's not the only type of thing that this interpretability work does, but this is the area where I have been primarily focused in trying to better capture and analyze the model's competence for meaning. Yeah, absolutely. And I focused so far mostly on this probing work, but that's less recent than work that I've been doing studying pre-trained language models and using more behavioral types of studies of the brain, looking at brain responses to words in context, and adapting those for diagnostics of the competencies of pre-trained language models on the basis of their ability to predict words in context. And so,
Let's dig in. Tell us more about that.
great, yeah, it's so this is work that so again more recently than the sentence encoders, we have these pre-trained language models that have, of course, exploded into the scene a couple of years ago and have really pushed the state of the art across most of our tasks quite substantially. And the real question that then trails behind this advance is. What is it that pre-training is giving to these models? What is it that they're learning? It seems the obvious interpretation is that some sort of pretty generalizable linguistic competence has been conferred on these models during the pre-training process, which then can transfer to many different tasks via fine tuning. And so the
And I think
question,
that if, to maybe jump in and draw the parallel, I think what we kind of want is something analogous to, the early research on convolutional neural nets that said, oh, at this layer, we're just learning textures. And at this layer, we're learning shapes. And at this layer, we're learning colors, that kind of thing. I guess more recent research said, well, really, it's all textures. But I think we want some kind of intuitive sense that these models are, learning something.
absolutely, yeah. So there is this very appealing idea that layer by layer will sort of increasingly abstract, increasingly sophisticated information being represented, and so the the work that I was describing there is less focused on examining the contents of the information encoded in individual layers, though there is even more recent work that does more of that with these more recent models. But this work takes a separate approach, a behaviorally based approach that says, all right, let's just look at the model's behaviors in the task for which it was optimized, that is
Mhm.
word prediction, and say, all
Mhm.
right, this is the fairest possible way that we can check what the model learned, because if the model is going to show competence in something, presumably it's going to be because it needed that information to optimize its objective, which involves word prediction. And so the reasoning there is, let's examine the model in its absolutely most natural setting. Let's see what its word predictions can tell us about how much it knows about the context, and how much information it uses in context to make a prediction. So an example that I often give is, and this is from a brain study, and I borrowed it and adapted it into a diagnostic for language models. He caught the pass and scored a touchdown. There was nothing he loved more than a good game of blank. And then we see the model's competence in being able to make a prediction here.
Mhm.
That case is actually one of the easiest items in the data set. Another one that I give as an example, which is a bit more opaque. I saw that my mother wasn't drinking her soup. Then I realized that she didn't have A, right? And then humans can infer what's going on in this situation and can realize that, okay, she has the soup already. So what she's missing presumably is a spoon, right? But this is quite a lot of inference for a model to handle. And so these are sort of difficult types of prediction tasks. And I drew on a number of different brain studies that sort of forced the models to use different types of information about the context to make their word predictions. So again, this is drawing heavily on inspiration from the brain side, adapting it in a way that allows us to ask questions in a very natural way about these models on the basis of the type of predictions that they naturally output. So yeah, so this was one of the clearest finding that the models did pretty well on certain things, very well on certain things. Probably the starkest finding was with respect to negation. you have sentences like a robin is a, they're very good at producing a word like bird, really good at associating robin with bird and hammer with tool and things like this. But if you add a negation, a robin is not a, now the appropriate continuation is just basically anything but bird, but the model still prefers bird over something like tree, right?
Mm.
So this was the so 100% of the time it fails to assign a higher probability to the true completion tree over the now false completion of bird, because it just really wants to associate robin and bird together, presumably. So this is the type of thing that I mean when I say we want to try to dig into how much does the model really understand the meanings of words and their implications and how they affect the context, versus just sort of being a really sophisticated associative pattern detecting device, right?
Hmm. You mentioned in there that these ideas you pulled over from brain science like force the model to be very specific in the, I guess, the question that it was answering, or the way that it was producing the result. Can you elaborate on the specific techniques or approaches from the brain science side that you applied in this case?
Sure. Yeah. So, in one sense in which I mean that is that these items were all hand designed by psycholinguists to target specific, to ask specific types of
Mhm.
questions about how and when the brain processes certain types of information. And another sense in which I mean that, and another sense in which I mean that is that in choosing these diagnostics, I had a particular criterion, which was the following. There are a couple of different indices of prediction in humans. One is you can give a human a fill in the blank task and just see what words they fill in. And then if you do this over a group of humans, you can derive a measure called close probability, which is just the proportion of humans that will fill in a given word in a context. So if I say, I like my coffee with cream, and probably a decent proportion of humans will say sugar, probably no humans will say socks. And so we're going to have a close probability, right, of maybe, let's say, 0.6 for the for sugar and probably 0 for socks. That is an example that's often used in psycholinguistics. So if you have a psycholinguist in your group, then maybe it won't be 0. But this is, this is mostly probably no one's going to put socks. So, um, but another index of sort of the brain's predictive processing is what's known as the N400 component. It's measured using EEG, and it seems to index something along the lines of fit of an incoming word to context. So if you have a very expected word, you may see a reduction in this component. Whereas if you see something that wasn't expected, then you'll see sort of a normal uh, large N400 component. And so this these two different predictive indices often align with each other in terms of indicating to us that the human was expecting a word was coming, or predicted a word in that context, thought that word was a good fit, etc. Um, but sometimes the N400 seems less sophisticated. Sometimes the N400 seems to be missing certain types of information. And my specific inspiration in using these studies was to see because the N400 seems to be a type of component that's probably, at least under some circumstances, reflecting maybe a little slightly shallower statistical processing rather than necessarily processing of all of the possible context information and the meaning. Um, Basically, I wanted to test whether these LMs, these language models, were going to pattern with the N400 and look a little more like this less sophisticated predictive brain response, or whether they would look like the sort of endpoint of human processing when the humans have all the time they want and they're doing a fill in the blank task. So basically, I was pitting these two mechanisms against each other and
Mhm.
seeing, and the studies that I chose were studies that specifically show a divergence between these two. So the closed patterns diverge from the N400 patterns, suggesting that the N400 is missing something. So the question basically was, the information that the N400 is missing, is BERT going to miss this as well? That was the basic approach there. And so the diagnostics were very carefully chosen to be sort of especially tricky and to test for whether BERT was going to be sensitive to these particular types of information. And in addition, they were designed in such a way to try to control the specific types of information in context that would drive the predictions that humans make in that context. So in all of these different ways, they were controlled to help us to ask more targeted questions about what the models are doing.
And what were the specific results relative to your expectation with this N400?
Yeah, so the comparison to the N400 was slightly complicated, and so I tend not to try to describe the results in a way that's too anchored to the N400. But basically,
Mm.
um, the models did not resemble the N400 completely, in that they did have reliable ability to prefer good continuations to bad continuations. And this was the key comparison to the N400. The N400 lacked a statistically significant difference between these conditions, even though one was a bad continuation in the context, one was a good continuation. So we're talking about things like he got the pass and scored a touchdown. There was nothing he enjoyed more than a good game of. Football is a good continuation here. Baseball is not a good continuation here.
Mhm.
Um, but the N400 shows some favoring of baseball nonetheless, and the theory is that it's because baseball and football are related to each other.
Mhm.
So in this sense, BERT was reliably able, in a majority of cases, not all cases, to prefer the good continuation to the bad continuation, but it did not match humans it wasn't able to match human close predictions very well, especially in one of the diagnostics where the we had role reversals, like the waitress served the customer served the waitress. It was able to tell the difference between these, but it wasn't usually able to predict the correct event. So the actual sentence was, the restaurant owner forgot which customer the waitress had blank. So
Mhm.
served is a pretty good prediction in this case, but the models were not great at matching the top human predictions there. The place where the model really did resemble the N400 was in its insensitivity to negation, in the fact that it uh, continued to prefer Robin over tree, even when that not the negation was in there. And that is something that does resemble the patterns that were seen in the corresponding N400 studies. So in some ways, it maybe did a little better, quote unquote, than the N400, but in other ways, it really did show the same types of insensitivities that probably are attributable to similar types of statistical associations that it learned.
Mm. I thought one of the directions you were going was going to um, talk about, I guess, completions that were valid completions but had some greater degree of surprise or novelty or something along those lines. Um, did I pick up on a spurious signal there?
Well,
I think you were describing the mechanism of the N400 or and the EEGs.
yeah, well, so we have basically two types of tests that we're using in these diagnostics. One is uh, prediction accuracy. So this is saying, if we look at the model's top completions, is it able to match the top human completions? So this is one
Mhm.
of the measures. Um, and so in that sense, there is a bit of it- there are probably various completions that may all be valid, but some are better than others. And so, in a sense, this is what the close probability is being used for, is to say, okay, well, what do humans think is actually the best, continuation here? In some cases, you will also ask humans for plausibility judgments and say, even if this wasn't your top consideration, your top prediction, is it an okay completion? But that wasn't really a consideration in this
Mhm.
study. And then the other measure that we're using is, there are sort of two different completions. One is clearly better than the other. And the question is, can the model tell that one is better than the other? So we're just looking at the relative probabilities and saying, does it assign a higher probability to the better completion? And so in that sense, it doesn't matter if it chose either of those as its top completion. It's just a matter of whether it chose the better, prefers the better one over the worse one. And so we're going from a couple of different angles in terms of assessing, looking at the model's word predictions and probabilities over the vocabulary, and seeing uh, what type of competence we're detecting on the basis of those predictions.
Okay, very cool. What's next in your research?
Yeah, so I have been continuing with the composition work. My student Long Yu has recently been working on looking at two-word phrase composition in transformers, and similarly has been finding if you control for word level effects, we're really not seeing very strong abilities of the models to align with human judgments of what the meanings of these phrases are and how they relate to one another. Um, yeah, so in general, what I think is one of the most important problems in the field right now is to improve our ability to successfully and accurately evaluate how well these models are capturing meaning. I think that meaning is, there may be some folks who will be less focused on meaning per se, just want to focus on answering tasks. But I do think that in the end, robust and flexible NLU is going to be dependent on being able to extract generalizable and accurate meaning information. And our ability to tell how well we're doing in terms of moving toward that goal is going to hinge on our ability to evaluate this in a way that teases apart the things that we don't want and the things that we don't count as meaning understanding and the things that we do count. So at the moment, that's the direction we're going. We're doing a combination of things to try to target things like the ability of the models to capture meaning in a compositional way, using both probing methods that look directly at the representations that the models learn, using behavioral methods that look at the predictions in a little more of a natural setting. Yeah, those are the types of directions we're going to try to answer those questions.
Awesome. Awesome. Well, Allison, thanks so much for joining us.
Thank you very much. It's been great to chat.
Awesome. Thank you.